All right, guys, it's about 10 o'clock. I think I'm going to go ahead and get started. It's good to see all of you. A lot of traffic getting to campus this morning, I tell you. I don't know. That State College Boulevard was backed up halfway up the hill to, I think, Baston Cherry Road. So at least I have office hours before class. I have a little buffer before I actually have to be up here. Hope you guys are handling the parking and the traffic and all that as well as possible, given how many people are around here. Let's see. I am excited, of course, as I always am about this time of the week, to talk about math for the next couple of hours. A couple of announcements. This shouldn't take long. We have a homework assignment due tomorrow night, and it's kind of extensive. I already told you to not do it when you're tired. Some people I know have gotten a really, really good start on it. If you haven't, you should definitely get started on it today. This is not one that you want to do at the 11th hour before you have to turn it in. So try to get an early start. If you have any questions already about it during the break today, if you want to add problem numbers over here, we can certainly do some of them together. We're also going to do some group work in a little while to practice some of the stuff that's related to that assignment. So hopefully that'll help make it a little easier. It's not that it's hard, it's just kind of tedious. That's the thing. You saw me doing those EROs on Tuesday. That's really what this homework has a lot of. So you just have to kind of hunker down and focus on it and do your best to try to not make too many mistakes, because those are frustrating. Oh, and I was going to mention, so just I think you guys all know that I have a lot of office hours today, but I'm actually going to add some tomorrow as well. So office hours today, basically after 5:30. I mean, I actually have a short little office hour after class. It's fine as well, but I only have like a half hour and I have to go do something. But after 5:30 today, I'll pretty much be around. I take a dinner break around 7 for about an hour. Other than that, I should be around. But I'm going to add some tomorrow as well. If you want to snapshot this, in the evening, I have to be here for an event that should get over about 7:30. And so by 8 o'clock, I should be down to my office. So really want everybody to do a good job on this assignment, and I'm here to help. I'll go over the answers with you. I'll help you solve any of the problems, whatever you need. So just let me know. It's just good practice. So yeah, I'll be available for those times. As you can see, I'm not a morning person. But other than that, I mean, I guess it's morning, but I'm barely a morning person. So that's why I always have these late office hours. I think that's it for my announcements for right now. There will be, of course, an assignment looming for next Tuesday that you can work on over the weekend. And that'll be based on a lot of what we're going to do today, actually. So that'll be the next thing to pay attention to once we get done with the current assignment as well. Questions? Any confusion about anything? We're kind of just rolling through things here, 3 weeks in. Yeah, so what I'd like to start with is bringing us back to where we left off on Tuesday. We had talked about this idea of an invertible matrix. And of course, a lot of matrices, in fact, most matrices are not invertible. So that's the bad news. First of all, the matrix has to be square size to even have a chance to be invertible, right? So if it's not a square matrix, then this section that we're talking about today doesn't even apply, right? It's got to be an invertible matrix. It's got to be a square matrix to even have a chance. And even then, when the matrix is a square size, it will be invertible only when you have another matrix, also the same size, and we're calling this A inverse, right? And the idea is that when you multiply A with A inverse in either order, the product should cancel out to I. Okay, I like to remember this definition well, because once we get into the nuts and bolts of answering some technical questions, it's easy to forget where it all came from. So I'm just putting this back up on the board again as sort of the definition of an inverse and a definition of a matrix being invertible. On Tuesday, I wasn't calling it A to the -1. In the original definition, I called it B. But you might remember on Tuesday, I won't rewrite it here, but we showed that there's only one inverse for a matrix. And so we might as well just write it as A to the -1. And that's a good notation for the inverse of a matrix. Okay, So this thing may exist. It says if there exists an A inverse, then we have an invertible matrix. And what's so great about that? Well, the application that I've so far given you, and there's going to be others, but this is just the first one off the tip of the iceberg, is that if we have a linear system that we'd like to solve for the unknowns x. So this is how our linear system can be written. We can write it as a matrix multiplication with the unknown values put into this vector that I'm calling x. In that case, if we have this kind of a linear system, and if we just get lucky enough that the A inverse exists, in other words, that A is invertible, hey, then we can actually solve for the unknowns by just taking that inverse and multiplying by the B vector that was on the right-hand side of the system. You're essentially, it's like dividing by A. We technically are not allowed to divide by a matrix, but the effect of this is that if A is invertible, we can move it to the other side of the equation to isolate the x, you see. So that's kind of a nice application. I'm going to do an example of that here in a little while as well. But we want to have a reason for doing stuff. We want to know why our invertible matrix is important, and we definitely at least have one on the board already before we've even done an example. Okay, so we're going to get to that. Is everybody okay with this? This is just a little summary of where we left off on Tuesday. I always come in and start with this just to kind of get us back oriented again with where we're at. Everybody good with all of this? Not too bad so far. Okay, well, I gave you my soap opera hook on Tuesday to get you to come back. Obviously it worked, you're here. By asking you a couple of questions that we might need to think about with respect to inverses. The first one is, if I give you a square matrix, an n by n matrix, how can I know if it's going to have an inverse or not? Right? Some matrices won't, right? How do I know that if this A inverse will exist at all, right? And then if it does exist, how can we even find it, right? So that we could then use it to help us solve these problems. So these are two really good questions that we haven't answered yet, and we're going to answer them today. All right. Turns out it's pretty easy to answer these two questions if n is equal to 2. If my matrix is a 2 by 2 size. So to kind of ease our way into this, I'm going to give the answers to these questions for n equals 2 first. I just want everybody to kind of know how this works for 2 by 2 matrices, which of course they come up a lot, right? The 2 by 2 size is pretty common, and so it makes sense to answer this for that first of all. So in this case, we have the matrix A is 2 by 2, and I'm going to kind of write it out with just some generic letters here, little a, b, and then little c, d on the second row. So let's take the A to be that. Okay, and then let's answer these two questions. So number one, the first question, how do we decide if A is invertible? Well, the matrix A, B, and then C, D is invertible if and only if, so I'm going to give you the condition right here, the easy condition, you will want to memorize this, which is that A times D minus B times C is not 0. So for a 2 by 2 matrix, this is the condition. Very easy. You're just playing with numbers here. You're taking A times D, which is actually the numbers on the main diagonal, and you subtract the off diagonal numbers B and C. And as long as that's not 0, then your matrix is invertible. You may already be wondering, well, why is that? We will see that. Okay, so we will see that here in a moment. But I'm at least just getting the answer down for you right away. This is so simple, I'm not even going to do an example of it right now. If I give you the 4 numbers in the matrix, all you got to do is calculate AD minus BC and see whether it's 0 or not. So in the case when it is not 0, right, when this AD minus BC is not 0, then how can we find the A inverse? Well, I could just give you the answer, which is what I'm going to do. Okay, so I'm going to give you the answer. You will want to memorize this one for sure, right? The inverse of A in this case, right? So I'm talking about this little a, little b, and then little c, little d inverse. The formula for it is, okay, so one little thing to memorize here, which is you're going to take 1 over AD minus BC. And then you're gonna make a matrix, it's also 2 by 2. And the important thing here, guys, is that you are going to swap the diagonal values. So the A and the D get swapped to D and A. The other two values, they stay where they are, but they pick up minus signs. So you have minus B and minus C. So here is another very nice formula. Anytime I'm putting stuff in boxes, it usually means it's important to not lose track of it. That's the formula for the inverse of a 2 by 2 matrix. Notice that obviously we're dividing out in front. So this is a matrix with a scalar multiple in front of it. So you're really doing a scalar multiplication. But obviously you would never want to divide by 0. So this is another way to kind of catch yourself as to when the matrix will be invertible. AD minus BC has to be not 0, otherwise this wouldn't have even made sense. Okay. I have a question for you about this, because so far you're just taking my word for it, that this is the right formula. What if you didn't believe me, or what if you weren't sure that this could be the right answer? Is there a way to check that this really would be the inverse of our original matrix A? Homan?
Multiplied by A.
And what are we supposed to get?
The identity matrix.
It's right here, isn't it? Yeah, if I multiply the A with the A inverse, we should get I. I'd like to actually do that with you. I'd like to check this, and there'll be a couple of the homework problems for next week that will be like that as well. Let's just do the A inverse times the A. I'll just do that one. And let's just see what we get. So the A inverse, I've decided to put it on the left, just kind of randomly choosing that. So I'll put the A inverse here first. That's the A inverse, and I'm going to multiply that by the original A, which is AB, and then CD. So I'm just going to calculate this. So when you have something like this, guys, you can leave that scalar outside in front and just do this matrix multiplication first. Let's just check it out. Let's check it out. So I'm going to leave the 1 over AD minus BC out in front. And now we have to remember the matrix multiplication that we learned about a week ago. You take dot products of the rows of the first matrix multiplied by the columns of the second matrix. And you have 4 of those combinations to do. Let's see what we get. When I do the 1, 1 entry in the upper left corner, I'm going to take AD and then minus BC. So AD minus BC goes there. All right. I'm hoping everybody's comfortable with the matrix multiplication. If you're not, don't feel bad about it, but you should do something about it. Come to my office hours. We can practice it again, because this has just got to be, this has to be just pretty much autopilot pretty soon. For the 1, 2 entry, I go across the first row here times the second column here, and I get BD minus BD, which adds up to 0. Okay. Now when I want to go to the bottom row, I start dotting the bottom row of this matrix. So in the lower left corner, I'll have negative AC plus AC. And then in the bottom right corner, I have negative BC plus AD. I write all of that down. And now what I'm going to do is I am going to shove this scalar into the matrix. So remember, the matrix multiplication, sorry, the scalar multiplication is done by just multiplying the scalar into all of the entries. So you can see that what would happen if you did that is that on the upper left corner, you'd get a 1. On the upper right corner and lower left corner, we still have 0. And here's AD minus BC again, canceling out with the scalar in front. And look at that. Look at that. We actually do get I2, the 2 by 2 identity matrix. So this is verifying that the matrix in this box up here really is the inverse of our 2 by 2. Okay? So as long as AD minus BC is not 0, we can write down this matrix, and we've now checked that it really does give us the identity. It's actually not necessary. I'm gonna add one more thing over here. I'm gonna put an equal sign, but I'm gonna write the word not necessary next to it, which is that it's not necessary to also check that A times A inverse is equal to the identity. If I've checked in one order that the product is equal to I, then for reasons that are a little deeper than I want to get into, the product in the other order will also be I. Remember, normally, we all, I hope, know this, that normally you can't switch the order of two matrices and expect the answers to be the same. So normally you might feel like just checking this is not enough to guarantee that you really have the full definition of the inverse here. But what I'm saying is that when it's checking an inverse and you have the product of two matrices equaling the identity in one order, then it will have to work in the other order as well. We could do it. I could do another calculation and check it for you, but it wouldn't be very interesting. I think I'll just leave it out. Okay. Is that okay with everybody? So if I hand you a 2 by 2 matrix, you should be able to tell me whether it's invertible or not. And if it is, you should be able to write down the inverse. Piece of cake. Okay. So that's the easy part of the conversation. The harder part is what if n is larger than 2? So now I need to talk about that. So for n greater than 2, unfortunately, I can't just give you a formula for the inverse or anything like that. It's got to be a whole conversation. So what we have to do is, so we need some background. So I'm not ready to just straight out answer the question yet. When the matrix is larger than 2 by 2, I kind of need to have a little bit more theory. So I'm going to make a definition here. And this definition will help start talking about how do we answer our two questions when n is bigger than 2. I want to define something called an elementary matrix. So an elementary matrix, I usually like to call these matrices capital E. So an elementary matrix is just any matrix that is obtained by applying one, I'm going to emphasize that, one ERO to the identity matrix. So the first part of this conversation is to understand what an elementary matrix is. You basically start with the identity matrix and you do one ERO to it. So I didn't put this in the recap, but the elementary row operations, we talked about those, yeah. We have 3 types. There's permuting 2 rows. There's multiplying a row by a non-zero constant. And then there is adding a multiple of one row to another. Those are the 3 EROs we talked about. So let's just write a couple of examples here and see if this kind of makes sense. So for example, I claim that we could have, let's just call it E1 because I'm going to do several examples. Here would be an example of an elementary matrix. Okay, so the first row is 1, 0, 0. The second row is 0, 0, 1. And the third row is 0, 1, 0. Does everybody agree that if I start with my 3 by 3 identity matrix, which by the way would be this, here's the I3, right? So I think we can all see that all I had to do to take this identity matrix and obtain this one is permute rows 2 and 3. So the specific ERO here, we would have denoted that on Tuesday. We had these notations. We would write that as P23. So far, so good. Let me give you another one, call this one E2. Maybe we have this one. I'm only gonna use this, I'm only gonna make it a 2x2 matrix this time. So I'm gonna use 1, 0, and 7, 1. So the question is, can we obtain that by doing one ERO to this identity matrix here? So can we take the 2x2 identity matrix and get this one by using a single ERO? What ERO would it be, just so we have it down as a reference? A12 of 7, exactly. So you take, remember how that works? You take 7 times the first row and add it to the second row. So 7 times the first row would give me a 7 in the first column, but we add that into the second column. Notice the first column, or sorry, the first row doesn't change at all. We're just using the first row to then change the second row. Right, so this is just A12 of 7. Let me just rewrite this a little bit nicer. A12 of 7. So these are examples of elementary matrices. Read.
Negative.
Actually, it's 7. It's actually 7. So if we start with our, if we start with this identity matrix and we go to here, we can just take 7 times the first row and add that to the second row, and it becomes that. Seem okay? Everybody good? Okay, so that's kind of how that works. So these are 2 examples of elementary matrices. Of course, there's billions of them, depending on what ERO you want to play with and what size matrix you want to play with, and so on. And I wanted to point out that you can actually use these elementary matrices to encode sort of formally the ERO that it was created from. What I mean by that is, so just as, I'll just say it, maybe I'll make a remark and talk about it with this example. An elementary, sorry, I say it this way. Left multiplying by an elementary matrix. If we left multiply by an elementary matrix, that has the effect of performing the corresponding ERO. So whatever the ERO is that is associated with our elementary matrix, if we left multiply by the elementary matrix, we are effectively going to perform the ERO. I can show you exactly what I mean. If we, let's go back to our 2 examples. If we take E1, I'm going to put it on the left here. So 1, 0, 0, 0, 0, 1, and 0, 1, 0. If we put that on the left of any random 3x3 matrix, A, B, C, D, E, F, G, H, I. So if I just take any old random matrix and I left multiply it by my elementary matrix, this is the elementary matrix from my first example here, then just follow me on this calculation. We go across the rows of the first matrix and dot them with the columns of the second matrix. What happens? Well, on the 1, 1 entry, we get A plus 0 plus 0. That would be A. Top entry here, B plus 0 plus 0. Next entry, C plus 0 plus 0. So the ABC is there. Now, when I go to the second row and I dot the second row with each of these columns, I get 0 plus 0 plus G, 0 plus 0 plus H, and 0 plus 0 plus I. And now if I do the same thing with the third row, and I dot the third row with the columns of the second matrix, I have 0 plus D plus 0, 0 plus E plus 0, and 0 plus F plus 0. And you can see what the resulting matrix is. It has had basically from here to here, you basically have done P23. right? So that was how this elementary matrix came about. It was associated with permuting the second and third row. So what effect does that matrix have on anything you hit it with? Oh, it permutes the second and third row of the matrix that you multiply it by, right? So you can kind of see that. We can do the same thing on the second one. I'll do this kind of quickly. It's a smaller one, just this little 2 by 2 matrix, 1, 0, and 7, 1. What happens if I multiply it by any old 2 by 2 matrix, A, B, and C, D? Well, let's just calculate it out. This is just good practice with matrix multiplication, right? Let's get a little extra practice this morning with that. So when I do this, started going across the rows of the first matrix and dotting them with the columns of the second matrix. We get A plus 0 in the upper left corner. We get B plus 0 in the upper right corner. And in the lower left corner, I have 7A plus C. And in the lower right corner, I have 7B plus D. So what has happened? Again, the effect of multiplying by this elementary matrix is that it looks like we added 7 times the first row to the second row. So that is exactly A1, 2 of 7. So if you don't like the elementary row operations, you can just exchange them in for elementary matrices now. And just do multiplication by the elementary matrices, and that has the effect. It has the same effect as just performing the ERO. Okay, everybody got it? So that's the definition of an elementary matrix. Again, let's not lose track of where we are. We're trying to answer these two questions, but for larger matrices. The 2 by 2 case is done. We have nice formulas in the boxes for that. But for larger matrices, we need some background. And this is the first part of that background, the idea of an elementary matrix. Okay, then let's come over here and talk about a couple other things. This isn't going to take that long, by the way. If you're thinking this is going to take an hour to get to the answer, it's not. It might take another 5 minutes. It's not really that bad. Okay, so let's talk about one more definition first, though. Definition. We say that capital A is row equivalent. So here's another word. It's row equivalent to B. And you'll see me sometimes writing that as A with sort of an arrow. I'll put the word row above my arrow here. So kind of A is row equivalent to B with an arrow going from A to B. If there exists elementary matrices, if there exists elementary matrices, so there might be several of them here, let's say E1, comma, E2, comma, dot, 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 up to EK. I don't know exactly how many of them I will have. It's just a list of elementary matrices with the following equation. You start with A and you left multiply it by E1 and then left multiply that by E2 and dot, dot, dot. Eventually left multiply everything you've got up to that point by EK, and if that equals B. Okay. If that then equals B. Let's not get too worked up over this. All this is really saying is two matrices are row equivalent. If you can start with one of them and do some EROs to that matrix and get the other one. Right? Because we just said that every time you multiply on the left by an elementary matrix, it's like doing an ERO. So here I'm doing K EROs back to back to back to back to back and ending up with something else. Actually, on your homework for tomorrow, on any of those examples where you started with a matrix and you did a bunch of EROs, every single matrix that's on that piece of paper is row equivalent to the one you started with. Because you started with it and you did some EROs and obtained other matrices along the way. Well, those are all row equivalent to what you started with. Okay, so this is actually not that deep of a concept. It just looks a little abstract the way I wrote it here. But if you are okay with that definition, then I'm gonna make a nice little note here that will help us to answer our two questions about inverses of matrices that are larger. Namely, if A is row equivalent to the identity matrix. If it's row equivalent to the identity matrix, that would just mean that over where the B is really the identity matrix. Would you agree that in that case, if A is row equivalent to the identity matrix, then what that would mean is that EK times dot 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 times E2 times E1 times A is equal to the identity matrix. So I'm just in the place where the B was, I'm just putting the identity matrix now. So in this case, would you guys all agree that A is invertible? I erased my definition. Remind you here, two matrices are invertible if when you multiply them together, you get the identity matrix in either order. Do we see an inverse for A in our latest equation here? No. Here's A, here's the identity matrix. So let's look at this side of it actually. With the A on the right, and here's the identity matrix. Would you guys agree that all of these E's together as a product is actually sitting in the spot where the A inverse would be? That's exactly right. A is invertible and its inverse will be all of those E's multiplied together, right? So A is invertible with, we can even write down the formula for it. The inverse of A will simply be all of these E's multiplied together. These are these elementary matrices that we just talked about. There is a formula for A inverse. Okay. Let me keep my questions up here for a second. All right, so this is obviously not as ideal as the 2x2 answers. For one thing, you have to spend a lot of effort to do EROs to try to bring A to the identity matrix. Even just getting it into row echelon form, which is the homework for tomorrow night, is a headache. Well, this is doing even more than that. This is taking it all the way to the identity matrix, and then we don't even know if it's going to succeed, right? And even if it does succeed, great. Okay, so I've done, let's say, 5 EROs to get A to the identity matrix. Then that would mean that the inverse of A is the product of 5 matrices over here. Do people feel like multiplying like 5 matrices side by side by side by side by side together? I think that'll get tiring in a hurry, right? So fortunately, I have a wonderful answer to that issue. So it is going to be some work. It is going to be some work, but it's not going to be as bad as multiplying a whole bunch of matrices together. I have a much better way to get A inverse than that. So here is what is called, I'm ready to answer my question, the questions now. This is called the Gauss-Jordan method for A inverse. 2 different mathematicians kind of figured this out independently, and they both are brilliant, and they both get credit for this method. Okay, so this is how we're going to do this. And it's 2 steps. It's just 2 steps. So that doesn't sound too bad. What we're going to do first, guys, is we're going to form the n by 2n matrix that looks like this. I'm going to draw it as a block structure. We're going to put the matrix that we have on the left side of that block. This would be an n by n matrix, right? Over here, this is n by n. And then on the other side is the n by n identity matrix. So taken as a whole, this thing has n rows, but it actually has 2n columns the way we've laid it out here. on the board. So we start by doing that. And then what we do, guys, for step 2 is we just apply EROs to the matrix. Right? Let me just write it out schematically. So you have, you start with the block that you formed in step 1. Okay. And then you probably remember from Tuesday that I used the little twiddle to do my ERO. But now I know that when I do an ERO, it's really like multiplying by an elementary matrix. That was this remark over here. So if I want to do an ERO, I can just do the corresponding elementary matrix. Let's say it's E1, and I apply it on the left of both sides. Does anybody know why I didn't write the I sub n on the part that's on the right side of that bar?
Identity matrix, so it would just be.
It's the identity matrix, which is like multiplying by 1. And so if we've said that a few times, so E1 times I is just E1. So I don't need to keep writing down the I. So we do that, and then I'm gonna do another ERO. I don't know what it is, so I'll call it E2. So now we have E2 times E1 times A on the left, and we have E2 times E1 on the right, and we're gonna keep going like that. I'm going to put twiddles with dot, dot, dot for a while, and eventually we will have done, let's say, K of these. So we will have E sub K times dot, dot, dot times E2 times E1 times A. And on the right side, EK times dot, dot, dot times E2 times E1. Now, if my note comes true, and if I was successful in taking A and using EROs to create the identity, that's this equation here, then at this moment on the left side, what do we actually have? We have IN. I'm just following I'm basically just copying this down. Now I said if it's successful. There is a big if in this whole conversation, right? If we cannot bring A to the identity matrix, that's just going to mean that it's not an invertible matrix. Okay, so you can try and try and try, but you don't know. But if you can get the identity matrix to show up on the left side of the bar, guess what's showing up on the right side of the bar at that exact same time? The inverse of A, right, which is already in this box, right? All of these elementary matrices multiplied together would be A inverse. That's exactly right. So that's it. That is the prescription for finding the inverse of a larger matrix. Now, I know what you're going to say. I know what you're probably thinking, which is, gosh, if the matrix doesn't have an inverse, let's say we don't know that yet. Somebody hands us a 4x4 matrix and says, I'd like to find the inverse if I can. Then you're going to start with this and you're going to hack away at it, doing ERO after ERO after ERO for who knows how long, trying to get the left side to become the identity matrix. And maybe it just isn't working. It's like, how long and how hard do I have to push and try to get there? That is a downside of this method. You don't know right off the bat whether it's going to work or not. And I know there's at least one problem on next week's homework where it says find the inverse if possible, and you're going to crank away and it's just not going to work. It's just not going to work out. However, that's a hook to get you to come back, again, because next week we're going to do chapter 3, which is all about something called determinants. And when we do that, we will have a way of testing directly from the get-go whether the matrix has an inverse or not. And then we won't waste our time looking for one if we find out right away that there isn't going to be one. Right. So that's something that has to come a little bit later. I think what I'd like to do though, first here, guys, is just practice this method. Okay, so let's just take an example and practice it. I'm just gonna say, let A be the matrix. I'm gonna make a 3x3 matrix here. 1, 0, and 1, and 0, and 1, and 1, and 2, and 3, and 6. The little 3x3 matrix, and what I'd like to do, guys, is if possible, find A inverse. If possible, let's try to find the inverse of A. Okay, so 3x3, we don't have a quick formula for it, so we're gonna have to just try out our method here, okay? So let me get this turned over here and let's try it. So we're going to do the solution. And we're gonna use this Gauss-Jordan, I'll just call it GJ method. We'll try the Gauss-Jordan method on this matrix. Okay, so the first step is to just set it up. So I'm just going to put my matrix here on the left side of a 3x3 block. And I'm going to augment it with the identity matrix, which is this one here, 1, 0, 0, 0, 1, 0, 0, 0, 1 on the right side. Okie doke. So we're going to start from that. And that's step one. Now from here, we just have to try to do EROs. The way you're going to want to do this is just what you were already doing in the previous section, which is to get it into row echelon form first. You can see that you already have a couple of pivots in those first two rows that are set up nicely. And it's really the third row that is not compatible with row echelon form yet. So would anybody like to suggest, just help me out here, with what would be maybe an ERO that we could start off with to try to get this into just row echelon form? Go ahead.
Add A,
Adding for which rows?
1 and 3,
1 to 3 of what multiple?
-2.
Of -2. I like it. Yes, so if we take net, and how is Marco figuring that out? He's just looking at these two numbers. He's saying, I want to turn this 2 into a 0 using this 1, right? So he's just doing that first column. So we're going to take, now how does this work again? We take -2 times the first row and we add it to the third row. It is only the third row that changes. So I'm going to start by recopying the first two rows the same as they already were, because those do not change with that particular ERO. And now I'm going to take negative, but do this in my head, -2 times the first row added to the third row. So that gets me that 0 that I want down in that lower left corner. -2 times 0 added to 3 is just 3. -2 times 1 added to 6 is 4. -2 times 1 added to 0 is -2. 0 added to 0 is 0, and 0 added to 1 is 1. So you're doing the ERO all the way across on both sides of the bar. So you just go all the way across that thing. I'll circle the pivots again. So far, we haven't made any progress on pivots, but we are getting closer. The first column looks great. Can I get somebody besides Marco to suggest a good ERO step that I could take from here? Yes, Adrian, right?
Yeah.
Go ahead.
Add the second row to the third row.
A of 2, 3 of what multiple?
-3.
-3. I like it. Yep. See the 1 and the 3 here? Right? I want to use this 1 to cancel out this 3. So let's do A2, 3 of -3. That does not change the first row, and it does not change the second row. But what it does on the third row, we have a 0, and then I take -3 times 1 and add it to 3, I get 0. -3 times 1 and add it to 4, I get 1. And then on the right side, I'll have a -2, a -3, and a 1. And now I'm going to circle my pivots here. We would have something looking like that. So we've got the left side into row echelon form. So far, so good. If I do anything before noon, there's a chance I could screw it up. So be sure to check me on this. I'm not a morning person, so I hope I'm doing it right so far. Okay, But now we're not done yet, okay? If we were just looking for row echelon form, we would say, yep, we're good to go. But we are actually trying to get all the way to the identity matrix. In this case, that means that these two ones have to be turned back into zeros. So I'm now going to add multiples of the bottom row to those upper rows in order to make that happen. So let's go up here and do another ERO. Let's do, what does anybody want to suggest? Suggest what I could do? To turn either of these ones into a zero by using the third row?
A, 3, and 2.
A, 3, and 2 of what multiple? Of -1. Yeah, I'll take the negative of the third row and add it to the second row. Guys, as we write this down, leave the first row blank for a minute. I'm not gonna fill anything in there yet. The third row stays the same. But I'm gonna take the negative of the third row and add it to the second row. So I'll have a 0, a 1, and a 0, and then a 2 and a 4 and a -1. So the negative of the third row added to the second row. Yeah. Okay. Can I do something else at the same time? Trevor?
You could do the same thing for row.
For row 1, exactly. I could do A3, 1 of -1. So if I take the negative of the third row and add it to the first row, I'll get 1, 0, and 0. And then negative of -2, when I add that to 1, it's 3. Negative of -3, when I add that to 0, it's just 3. And -1 added to 0 is -1. So let me just check my notes and make sure I have that looking the way it should. I think that looks pretty good. Okay, so guys, we were successful in making the identity matrix on the left side. And that means, if you believe my Gauss-Jordan discussion, the theory we did a few minutes ago, here is our A inverse, right here. That's the inverse of the matrix. So we have just found our first inverse of a 3x3. Yeah, if I didn't believe that, or if I wanted to check that, would there be a way to do that? If I was nervous that I screwed it up, could I do anything to check my answer?
Multiply by the original.
Take your proposed A inverse and multiply it by the original matrix. What are you supposed to get? Identity, right? That's the big thing, right? If you take A inverse times A, you're supposed to get the identity. So you could check it. Let's just take my word for it that we've done it right. I've got it in my notes. If I didn't do this right, I've been using these notes for a long time. There'll be a lot of confused students going back many years. I'm pretty sure this is the right answer, okay? Now, I'm gonna ask you a quick little follow-up, and then we'll be in pretty good shape on the computational aspects of this Gauss-Jordan method. So what if I asked you to solve the following system? X plus C equals 7. Y plus Z equals -1. And 2x plus 3y plus 6z equals 2. Let's say that I asked you to solve that system. Back over here. Now, on Tuesday, we learned the Gaussian elimination method, where you just put it into an augmented matrix and do EROs, and then based on where the pivots are, you can solve it. And remember, guys, that every linear system, oh, maybe you guys can remind me. What are the possibilities for how many solutions a linear system could have, just in general? Yes, Ryan. 0, 1, or infinitely many, depending on where the pivots are. I think maybe after the break, we'll practice that again. In this case, we don't know yet how many solutions we have. So we could just do what we did on Tuesday, put it into an augmented matrix and run with it, right? However, there's a reason this is a follow-up to what we've already done, and that is that if you look closely, guys, the coefficients in the left side of that system over there are exactly these values. Right? The 1, the 0, and the 1, that's 1 times x plus 0 times y plus 1 times z. Right? And the same thing on the second and third rows. So really, what we're saying is that our system can be expressed in the following way. 1, 0, 1, 0, 1, 1, 2, 3, 6 times the unknowns x, y, z. And this would be equal to whatever numbers I gave on the right side over there, which is 7, -1, and 2. And this is exactly the A that we were just working with. So since we've already done all of the blood, sweat, and tears in blue over here to come up with the inverse of A, let's not redo all of that. Let's just go straight to the answer. Does everybody remember how we do the answer? So if we have a system, put it up here in this box again, if we have a system, A times X equals B, which is basically what I'm giving you here. Here's my X vector, and here's my B vector. If I give you that, do you remember what the formula for X was?
Inverse times b.
The inverse of A times B. Yep, and of course that's if the inverse exists, but here it does, because we just did it. Okay, so this tells me then that X, Y, Z, which is my vector of unknowns, is the inverse of A. I guess I'll just write that first. A inverse times B. And then I know what A inverse is. We did it in the first part of the problem there. So what does that say? 3. Is that a 3? 3, 3, 3, -1. Sorry, my eyes are failing me here. 2, 4, -1. And what does that say on the bottom row?
-2, -3.
Okay, -2, -3, and 1. Thank you. Okay, so that's my inverse matrix, and I multiply that by the B, which is just the 7, the -1, and the 2. And now I just do the matrix multiplication here. That's all I have to do to get my answer. So 21 minus 3 minus 2 adds up to 16. 14 minus 4 minus 2 adds up to 8. And -14 plus 3 plus 2 adds up to -9. So those are my X, my Y, and my Z values right there. And so you'll remember I usually like to write the solution nicely using a set notation here. So we'll just put the answer into these braces. Something like that. Everybody good? So if I change the B vector, but I keep the coefficients the same, it's a super fast thing to get the new solution to my system. Maybe you're working on some real world problem that always uses the same coefficient matrix, but the input of the B vector changes a bunch of times. Well, you don't have to keep recalculating the solution using an augmented matrix. You could just take the inverse of A and just change this part. Just change the B vector, and then you'll very quickly spit out the new solution. It's really efficient, especially if you're using the same matrix over and over again. By the way, the other thing that kind of tells us, just kind of make this last thought here before we take a little break. So we just said, somebody reminded me, Brian reminded me a minute ago, that every linear system, as we talked about on Tuesday, has either no solutions, one solution, or infinitely many solutions. But when the system has a coefficient matrix that is invertible, like this one does, this coefficient matrix is exactly this, and that was invertible. We even found the inverse, right? When the coefficient matrix is invertible, we actually know that we are going to be in this scenario, right? We will get one solution because we actually know what that one unique solution is. It's just this guy. It's just this guy right here. So if you have an invertible matrix, you should not be getting pivots going into the far right column. And you should not be getting any free variables. Remember on Tuesday, we talked about that. If your system has unpivoted columns, which gives you free variables, you'd have infinitely many solutions, okay? That shouldn't be happening for an invertible matrix. And also, if your matrix is invertible, you should not be getting a pivot that's drifting into the far right column. Oh, I think, I'm gonna do one more thing before we take a break. Because it's quite pertinent since I'm talking about this now. And then we'll take a little break. We're gonna start today on probably the longest theorem in the book. It's actually got an entire section devoted to it, so I'm just going to write it here. This is a very short section. There's not even gonna be any homework on this section. It's just a single thing. And it is something called, it is a very famous result in linear algebra, guys, called the invertible matrix theorem. So what we're gonna get now, guys, is a little bit of theoretical side of this, okay? So I'm gonna give you some theory. Let's let A be an n by n matrix. What I want to say here is the following are equivalent. The following are equivalent. And what that means when I say the following, I am about to make you guys a list of a bunch of statements. And all of those statements will either be true about the matrix that we have or not true. Okay, so the first thing in the list is just going to be the statement A is invertible. So of course your matrix is either invertible or it isn't. And if it is, if your matrix is invertible, then everything else that I'm just about to write down in a moment will also be true about that matrix. And if A is not invertible, then everything I'm about to put in this list would not be true about your matrix. Okay, so this is really, really nice way to kind of put it all in one place in a single list, a whole bunch of theory. Okay, so the first one here, part B, is the system A times X equals B, right, has a unique solution for X. One solution, unique means one. One solution for X, and we even know what it is. I'll put it over here on the side in parentheses. It's A inverse times B. So if the matrix is invertible, then anytime you have a linear system that goes with that has that coefficient matrix, it will have a unique solution. That is the situation of the follow-up question that we just did. Right? Here's our linear system. The coefficient matrix was invertible, and yep, we only had one unique solution, which was this right here. Okay, so that's got to be true. Let's write down the next one. The next one is the system A times X equals 0. So the only thing I'm changing is I'm changing the B to 0. So don't change your notes necessarily, but just imagine with me for a minute if these had all been zeros, if the B vector was 0. So that would have meant again, don't change your notes here, it'll be really confusing. But if these were all zeros, which would have meant that these were all zeros, what would we have gotten for the matrix multiplication now? 0, 0, 0, right? Right, so this system, if A is invertible and you sort of cancel the matrix, right, it has only the trivial solution, that's what it's sometimes called, the trivial solution being X equals 0. It has only the trivial solution. Okay, so that's an important statement. So that's a couple of statements about systems that have your invertible matrix for the coefficients. But I have a few more things. Let's go to part D. Maybe you guys have a theory for me on this. Somebody wanna propose maybe what should be let's remember what the rank is. The rank is the number of pivots in a row echelon form of that matrix. So if we have an invertible matrix that's n by n, what's your thoughts about how many pivots you would have? Read?
N.
I think it's gonna be n, don't you? If you even look at this example, here's n equals 3. It's a 3 by 3 matrix. Look how many pivots you came up with. 3, right? So the rank is n. And see, that makes sense, right? If you had had less than 3 pivots, if you had had only 2 pivots somehow, then what would have happened is you would have had a free variable now. Well, if you have a free variable, then you would have had infinitely many solutions. You're not in the same conversation as you would for an invertible matrix. An invertible matrix should not have any free variables. You should have pivots that go straight down the diagonal, all the way from the top left to the bottom right. Okay, a couple of more. Part E, A can be expressed as a product of elementary matrices. I will tell you now that we really won't need this one. I probably won't mention it ever again. It's not that important, but if you really want to get a gold star and make sure you're feeling good about all of today's lecture, go back to the notes right before I explain the Gauss-Jordan method and see if you can see where the invertible matrix would be expressed as a product of elementary matrices. So the elementary matrices are not going to be hanging around very long. I just brought them in just to kind of explain that Gauss-Jordan method, but we don't really need to keep bringing them up. So that one is maybe a little less relevant. The next one is definitely shouldn't be any surprise, which is that for an invertible matrix, you better be able to do EROs and bring it to the identity matrix. So it should be row equivalent to the identity matrix. That's for sure. Okay. And you can see that, like in this example, it is. You start with A and you do EROs to A, and eventually it becomes the identity matrix. See, all of these matrices that I'm circling, they are all row equivalent to A. You just started with A and you did an ERO to them. Yeah, so that certainly should be reasonable. Okay, this invertible matrix theorem is actually in the, for those of you who do have a hard copy of this book, it's in the back flap cover of the book down here. And what you'll notice about it is it has part A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. This is only week 3, right? We have lots of time to work our way through this alphabet. Because yeah, we will be talking about this theorem again later. Some of the other statements in that list, we just don't know enough about those concepts yet. But once I've explained those concepts, don't be surprised when I circle back to this theorem and say, hey guys, let's tack on a few more things about invertible matrices. That's going to be what we're going to do. So this is all that I'm covering for you in section 2.8. Okay. There's no homework on this. This is just a conceptual sort of theoretical thing. But it's definitely good to try to understand these relationships. Questions? So far, so good. What we don't have in this list anywhere is a user-friendly item that will tell me just easily whether yes, it's invertible or no, it's not. I don't want to have to figure out if A is invertible all the time by trying to figure out its rank. That means I got to do a bunch of EROs. Or by trying to bring it to the identity matrix, which is also EROs. Or by working with systems and trying to solve it. That's also a lot of hefty EROs. So we're going to be looking for a statement G that's gonna come pretty soon, that's gonna give us a nicer, completely different way of testing for invertibility that has nothing to do with EROs. And that'll be kind of nice, so. Okay, this is a good time to take a break, I think. Let's take 10 minutes, let you stretch your legs, get some water, whatever. If you have questions on the homework for tomorrow, you can write them on the board during the break. And we'll come back in 10 minutes and pick things up. You're gonna like tumble over backwards. They don't have any support, do they? You're probably sitting in one that's maybe, I think, if you can lean that far back that easily, it's probably, it needs to be tightened. No, I've had the same, I'm pretty much a toothpick and I've also had trouble in those chairs.
They had one of the, two things that felt like an impress. I know it was really fun.
Right now.
I don't clap for plane. It's like so fire alarm.
And then.
You should write that.
I know.
Five in the morning.
No.
Bro, it doesn't go up.
Rank of, like I don't remember either, that's not rank of.
Oh. You get more per box.
That's it.
Oh, really?
There you go. Great.
Or in the back.
Oh.
School $5. Under, yeah. But that doesn't count as oh, that's the one.
Those are really good photos, bro.
Yeah, that's this is
You
see this guy? Do you see this?
Well, he does like so much.
This is testing.
Because this is like sports category.
I think that's the video. He works LinkedIn 30.
Oh.
But yeah, I don't know. I don't know. I think it's just. I couldn't tell that was you with the video. It's his only video of doing this. That's so weird. It says only, like, oh no, it's this one. Is he not here? I think so. Because there was. Was that it? You know? No. Somewhere, so everyone's like, he's exploring this game. But like, you put like a sticky thing on top of it, and like a metal thing that like pulls it open. It helps you breathe. Yeah, I see.
Yeah.
Have you seen the they're just like mush.
Probably.
It's all pretty negative. Maybe I'm balls lower. I think like the thing.
The word thing is find out something too. I do.
Where you at? It's clicked your data, it's clicked it in the page. Like, go back, it's a big one. No, no. That one, that one. That's one to do it. I had to go.
Hey.
Yeah. So number 4, I'm sure where if I went wrong anywhere.
This is the answer you got,
Here's the answer that I got.
and do you know if it's right or not?
I plugged it in. I plugged it in.
It's not working?
working.
Ooh, so something must be email. Let's see. One of the problems that sometimes people have is they just like, they don't copy it correctly. Looks like you copied it correctly. Um,
Oh.
So far, that looks fine. Then we're going to. So that's fine, and now we're gonna do A to A, which is what I would do. Should be fine. So Z equals -1. And then 2. For Y. For X.
That's why I'm asking if it's okay. They're little dust.
So X plus 4 minus 1 equals 1. X plus 4. So X plus 3 equals 1, which means X should be -2, not -4. I think that's your problem. I think it's just this equation here. You have Z correct and you have Y correct. Then when you solve for X, I think you made a little mistake. I'll let you check that.
I know where the town center should be, but I just don't. He said I never had a. It's seafood based. People will want.
But you got mine. Did I say?
Yeah, well, I don't, well, yesterday, I came back, I drove like, you might not know, this is true, I only sent you Tuesday.
Oh, okay.
50 miles.
Oh,
Yeah, you like, Nathan, so.
You made a special trip.
Yeah, right after work, I came in and talked about it, he was gonna be back.
Uh-huh.
And he was like, yeah, I'm very good, I'll go talk to him. And he sent me an email today saying. You know,
Oh.
and so I think my option is just gonna be. I have to be able
No, it's too much driving. I'm sorry to hear about all that.
It's all right.
Sorry. Imagine all those.
Yeah, no, I.
Some of There's all those people.
I started like three, four.
More full.
Yeah.
Okay.
It's a. It's.
So.
Yeah.
Okay.
Oh, yeah, you were there.
Just one more shot.
I you do that. This is.
Brianna.
My mother or father? No. That's how it is.
Oh, that's right.
Was it good? But it's had a, I think he had a relation where. I guess something. He's good.
I did my RFID, so
He took over. So we don't know if it's bringing. See, week.
Okay, guys, I think we've got just about everybody's made it back now. I hope so anyway. Looks like we got a blank board over there on the homework list. I'm assuming that either means that everything's perfect and everybody's done, or else it just means that people are still getting working on it. Or it's still, oh, we're still walking over there. Okay. Ah, I see. Got it. Okay. What in the world? Oh, the true false? Okay. I was like, what is he writing? Anyway, before we get to any of that, I wanted to present this, this is a more theoretical result that is actually good for reinforcing something I've been talking about from the beginning of this conversation, which is this theorem. And it just says that if you've got a couple of matrices that are already invertible, okay, so you already know that A and B are invertible, then what you can do is you can multiply them together and it will still be invertible. Or you can take a transpose and it will still be invertible. Now it's kind of interesting, the formulas here for what the inverses are. So if I want to know, well, what actually would be the inverse of A times B? It's, remember, invertible just means that this thing exists, right? So there exists an inverse to A times B. Interestingly, the formula for the inverse of A times B is actually B inverse times A inverse. And remember that the order of matrix multiplication is important. It matters, and we have to put it in the correct order. So make sure you get the B inverse on the left of the A inverse on the right side. By the way, have we seen anywhere else a property like that? Where when we had two things multiplied together and we did something to it, we had to switch the order of them? Another property, it was about a week ago that I talked about it. Do you think you might know what it is, Holman? Yeah, do you remember when I did the 10 properties of matrix algebra? the very last one, maybe I'll just put it over here. The very last one was that if you take A times B and you want to transpose it. Right, so this goes back a few sections, but it turned out that for that, we also had to switch the order of the A and the B. So it's just kind of nice to remember that, and it is the same kind of phenomenon with inverses as it was for transposes. Transpose is a little more basic. Remember, that's just switching rows and columns, swapping the rows and columns of the matrix. So if you do that with a product of matrices, you have to transpose them separately in the reverse order. Okay, and same thing for inverses, as it turns out. And then speaking of transposes, if a matrix is invertible, its transpose will be also. And the formula for the inverse of that transpose will be very natural to just take the inverse of the original matrix and transpose that. Okay, but what I really would like to do is prove these little equation for you, because it's good practice with some things I've been emphasizing about in inverses so far. So let's do the proof, and these will both be very short, by the way. I should be able to do this all on this board. Let's see how it goes. The first one is, I want to prove that the inverse of AB is equal to this thing over on the other side. How can I prove that the inverse of one thing is another thing? How do I prove that if I wanted to convince you that A and B were inverses of each other, what would you do to confirm that? Without calculating the inverses of the two matrices, can I just take the A and the B and I want to show that they are inverses of each other directly? How can I do that? Remember that 3 by 3 example we did before the break, and I had the answer and I said, well, if you wanted to check your answer. So I came up with the A inverse and I said, well, maybe you're worried you made a mistake. And if you wanted to check your answer, how would you check your answer? You have two matrices, you want to check. You don't want to calculate their inverses. You're claiming they are each other's inverse. How do you check it? It's the definition. Okay, this is a big deal. So let's just make sure we are all on the right page with this. Two things are inverses of each other if, when you multiply them together, you get what? The identity matrix. That's actually the definition of two things being inverses of each other. So that's the point I'm trying to make. And what we're going to do here is we're going to try to convince ourselves that the inverse of AB is B inverse times A inverse. So all I'm going to do is multiply together those two matrices. I'm going to just set them down side by side. I'm going to put AB first. And then what I claim its inverse is, if I'm right in my formula, is that the inverse of it should be B inverse A inverse. If you want to understand it just kind of from a nuts and bolts perspective of how you actually do these things, what you're really doing is you're setting down the matrix on the left, but without the -1 exponent on it. You notice that? It's just AB, because the inverse of AB is supposed to be this. And if I'm right, then after a little bit of algebra, and I always know how much space to leave, I should get to the identity matrix. Okay? So this is what we're going to do. We're going to check this out. So this guy times this guy, I can put parentheses here if I want. This guy times this guy should be I. Let's check it and make sure that it does work. Does anybody have a suggestion what I might want to do with the expression I have on the left here? It's so abstract, it can't be that hard. It can't be something really long and technical. It's going to be something very, very simple. Do parentheses matter with matrix multiplication? Didn't we say somewhere along the line that A, B, C is the same as A times BC? Doesn't even matter how the parentheses are grouped. Yeah?
Move the A's next to each other and the B's next to each other.
To do that, if I wanted to move the A's next to each other, I would have to switch the order of something, and that gets me into linear algebra jail really fast. Cannot do that. That's illegal. So you cannot switch the order of anything, but you can move parentheses around. So is there a good way to do the parentheses here? A, B, B inverse A. How about I try to emphasize in the middle the B inverse? That's what I actually want to do. Because what is B times B inverse? The identity matrix, right? Two things that are inverses of each other always becomes the identity matrix. So this is just A times the identity matrix times A inverse. Now the identity matrix is like multiplying by 1. So I can kind of just drop it. Okay, so that would just, if I drop it, it just becomes A inverse. So just get rid of the I. Don't need it. And what is A times A inverse? It's I, right? Guys, I always put one of these on my exams. You can almost take it to the bank. There will be something like this, sort of abstract, where I basically say, I want to see if the student really understands what the definition of an inverse is. It's one thing to go through the motions of the Gauss-Jordan method, which is just a bunch of EROs. This is understanding kind of where the whole concept comes from. So you take your two matrices, you set them down side by side. You don't switch the order of anything. You just try to simplify it down to I, which is exactly what we just did. Okay, let's try the second one. The second one is the A transpose. So what this is saying is the inverse of A transpose should be this thing on the right side. So I'm going to do it, set it up the same way I did for the first part. I'm going to take the A transpose, which is on the left, without the inverse on it, but I'm going to multiply it by what I'm saying that its inverse should be. So if this calculation, again, if this one comes out to the identity, which it should, then the inverse of one of those matrices is the other one, which is exactly what I'm trying to come up with. See what I mean? So I need to multiply this out. And it's done on an abstract level. That's why it's a one-liner. This is a one-liner as a solution. So I need to multiply this out and hopefully have it become I. Does anybody have a suggestion with what I could do with this first thing I have right here? This is something transpose times something transpose. Do we have that anywhere else on this whiteboard? Within the four corners of this whiteboard? Something transpose times something transpose. Yeah, it's hiding over here. There's a reason I wrote this down, right? So something transpose times something transpose. This was from earlier, right? This is one of our earlier properties. What's it say? It says I can make it into a single transpose, but I have to switch the order of the matrices inside. So I'm going to do that. I'm going to make a single transpose, but I'm going to switch the order of the two matrices. So the A inverse goes to the left and the A goes to the right. So I switch the order of those. Okay, so the A inverse was on the right and the A was on the left. If I pull the transpose out, which means I'm going like this, I can pull the transpose out. I have to switch the order of the matrices. What can I do with this? Read? Yeah, the A inverse times A, we see that. It's like knee-jerk reaction, it's equal to I, right? So this is just the identity. It still has that transpose on it. And let's just remember what the identity is. We haven't really written it down today. It's just this matrix that's got ones on the main diagonal and zeros everywhere else. What happens when you transpose that? If you flip it along this line, nothing happens, right? It just stays the same. It stays the same. So the transpose of the identity matrix is just the identity matrix. You can put checks on both of those. Okay. So anytime I ask you to show that two matrices are inverses of each other, what are you gonna do? You're gonna multiply them together at face value, simplify it down, hopefully to I. That's how you have to do it. Okay? Good enough? Questions here? Okay, if not, let's see, can you be specific about, there's a question from 2.5 on the true false read. Did you have any specific? I don't even remember which ones I asked about.
B, C, D, E.
B, C, D, and E, all of them. So you guys, just to remind you, please do write reasons for the true falses when you're turning those in. If my grader grades a true false, he's not just looking for the answer. All of the answers to the true false are in the back of the book. So you can at least know whether it's supposed to be true or not. But then it's just a question of whether you have a justification. We should have a justification for it. Oh yeah, so part B, I should definitely do. So this is the true false. What the statement is it says a homogeneous linear system, and I realize now I've done something bad, which is I have not told you what a homogeneous linear system is. So that's okay. This isn't a big deal. It is always consistent. So the question is that true or false? So if you go looking in the back of the book, it'll tell you that it's true. But we have to give a reason. And before we can give a reason, we have to know what we're talking about here. A homogeneous linear system, guys, it just means that word homogeneous gets used so much. We already saw it in the differential equations, and now it's showing up here. That just means that you're talking about a linear system that has 0 on the right side. So a homogeneous linear system is just of this form. Instead of AX equals B, specifically the right side should be all zeros. And the question is, will that always be consistent? Meaning, will it always have a solution? And I think the answer should be pretty clearly that it does. In fact, it's even talked about right here, that the system AX equals 0 should definitely have the solution of just all 0. The point here, though, was that it's only the trivial solution. There's no other solutions. But for sure, if you plug in 0, I mean, if you guys know this, if I write down any system of equations, and if every single equation is equal to 0, and I ask you to solve this for X, Y, and Z, that's a homogeneous system because all of the right sides are all 0. Everybody can look at that and just at a glance, you know one solution that would definitely work, which is to just make every single variable 0. So, and that's what this is here. The trivial solution is just the X vector equals 0. So your justification here, if you want to write down a justification, which you should, would just simply be X equals 0 is a solution. That's all you have to write. Okay, easy peasy. Okay, so that's that one. Part C just says, okay, so there's a lot of writing here and I don't want to write it all out. AX equals B, that's your form of your linear system. It just says, the statement is every column of the row echelon form of A corresponds to either a leading variable or a free variable. So every column of your row echelon form either corresponds to a leading variable or a free variable, but not both of your system. So if you remember on Tuesday, we talked about the unpivoted columns of your row echelon form give you free variables, and the pivoted columns correspond to the leading variable. So this is also true. This is very true. This is really just for justification, you could just say what I just said, which is that leading variables are lined up with pivoted columns. So very short, and then free variables correspond to unpivoted columns. Just something short like that would be more than enough. That's it. It's just that simple. So obviously every column either has a pivot or it doesn't. So you're gonna be in one of these two scenarios, no matter what. So that's also true pretty easily. Okay, what else do we have here? Part D. Let's see, part D just says, okay, so it just says that the system, again, it's another just little conceptual question. If we take AX equals B, it is consistent if and only if the last column of the row echelon form of, and they basically are talking about A sharp, they write it as A augmented by B, is unpivoted. This is what part D is saying. The last column, of course, is going to be the one that's on the far right side of the bar. Right, so this is really, you're taking A, you're augmenting it with the B vector, right? That's what A sharp is. So you do your EROs on this, and it's saying if the last column, meaning this one, is unpivoted, that your system is consistent. Is that true? Should take a vote. How many people think it's true? Okay. How many people think it's false? Kind of a little bit of a disagreement about it. So consistent just means there exists a solution. So what was the situation when we would not have any solutions? You have the 0 or the 1 or the infinity. What was the situation when you had no solutions? How did that show up in terms of the pivots in the final, row echelon form thing?
There was a pivot in the augmented column.
Exactly, when there was a pivot, this happens when there's a pivot in the far right column. So as long as the last column does not have a pivot, then we would have either one or infinitely many solutions, which would be consistent. So I would say that this is also true, because of basically that reason. Consistent. Well, actually, let's just say it this way. Let's say it's true because a system is inconsistent. I'll just kind of phrase it the opposite way. Inconsistent if and only if there is a pivot in the far right column. I like just saying it that way. Yeah. Okay, so that'd be a good enough reason for me. Again, I'm not looking for anything long. You don't need to write a big essay, just a quick sentence, something like that, would be great. Okay, and then part E. It's kind of funny, these are all coming out to be true so far. Part E, a linear system is consistent, so it's almost the same thing. AX equals B is consistent. So for part E, it just says if and only if there is a free variable. I won't write out all the words here. There is a free variable in your corresponding augmented matrix. Would that be true? So again, if we look at our three scenarios, the three outcomes here, right? These two are the case of consistent. It means there's at least one solution. And this is the one that's inconsistent. So is it true that in order to be consistent, we have to have a free variable? I don't think so, right? Because you can be consistent, but have just one solution only. If you have one solution, that's consistent, but there's no free variable. Remember, anytime you have free variables, you'll have infinitely many solutions. Right? So this one is actually false. And for a justification for that, I might write something like a system can have just one solution. So in that scenario, you're talking about a consistent system without a free variable. If that makes sense. That kind of look okay? All right. That look good? Good on the true false there? That kind of help a little bit? Yeah, kind of got that all taken care of in just a few minutes. I was gonna do some group work, but you know, we don't have a lot of time. I think I might save it until Tuesday. Because what I can do instead is the other thing that we're basically done with chapter 2, which is what I had hoped to do. But there was one thing I skipped on Tuesday, which I do often ask people on exams. So I thought maybe I should practice one of these with you. And there's also some of this in section 2.5 on the problems from 2.5. So let's do, maybe for all of our benefit now, this is a good time to just do one last example, and then depending on how this goes, we might even get done a little early with everything that I was hoping to do. So let's determine values of K such that the system below has, and so for part A, I'm gonna say 0 solutions. For part B, I'm gonna say 1 solution. And for part C, I'm gonna say infinity solutions. So this is good timing. The 3 outcomes of Gaussian elimination. And remember, I do have a YouTube video as well with about a 12-minute conversation about it. So over the weekend, if this is something you want extra guidance on, you can certainly look at that. Let me give you the system here. X plus 2y minus z equals 3. And then my second equation is going to be 2x plus 5y plus z is equal to 7. And then the third equation is going to be x plus y minus k squared times z equals negative k. So there's a k in the last equation, and the problem is asking us for which values of k will we get each of our 3, the 3 outcomes of Gaussian elimination. Okay. Does anybody have a suggestion how we should start off on this problem? You know what the answer to every question is in Math 250B? If I ask you almost anything in this class and say, what should we do? The answer by the 12th, 13th, 14th, 15th week of the semester, you're going to be like doing this in your sleep. The answer to everything in this class is put it in a matrix. Put it in a matrix, right? Here's your system. Let's just throw it into a matrix. So that's exactly what I'm going to do. I'm going to come over here and I'm just going to make an augmented matrix. I'll call this A sharp. And I'm just going to take my coefficients and lay them out into this matrix. So 1, 2, -1 augmented with 3. And then 2 and 5 and 1 augmented with 7. And then 1 and 1 and negative k squared augmented with negative k. And my unknowns are lined up with these columns on the left, right? So we'll keep track of that as we go along. But really, to decide whether we have no solutions, one solution, or infinitely many solutions, we really just need to bring this into row echelon form, do our EROs, right, and see where the pivots end up. It's all about the pivots, right? We've been talking about pivots everywhere. Pivots, non-pivots, whatever. It's always a big part of the story about how many solutions you have, right? So let's take a look at this. we're gonna do some EROs. This isn't gonna be too terrible. I've got my first pivot in the first column already in good shape. I wanna get zeros below this. Your first priority, guys, is to get zeros below whatever pivots you have. So in this case, I need to turn this 2 into a 0, and I need to turn this 1 into a 0. And I'm gonna do them at the same time, because I'm gonna do the A12 operation of what multiple should I use right here? -2, right? Exactly, I'll take -2 times the first row, I'm gonna add that to the second row, and then I'm gonna also, at the same time, do A13 of -1. So let's do both of those. The first row stays the same. Yeah, the first row stays the same. For the second row, when I take -2 times the first row and I add that to the second row, I should get 0 and 1 and 3 and 1. So -2 times the first row, fully being added all the way across to the second row. And then I'm gonna take, and stop me if I make any mistakes, okay? The next thing I need to do is take the negative of the first row and add that to the third row. So I'll get 0 here. -2 added to 1 is -1. Negative of -1, that would be 1. I'm gonna add that to -k squared, so it becomes 1 minus k squared. And then negative of 3 added to -k just becomes -k minus 3. So you're just going through the motions like you ordinarily would. The k is there, but just don't flinch. Just do it exactly the way you would do it if it was a regular number there. Okay, now I've got my pivot here. And then the next thing I need to do is, what ERO would you suggest at this point?
A23, what?
A23, I'm gonna use the second row with a multiple of 1 and add it to the third row. So I'm just simply going to add the second row to the third row. That means the first row stays the same. The second row stays the same. And I'm gonna add the second row to the third row. So the third row will become 0 and 0, 4 minus k squared, and -k minus 2. So I'm adding the second row to the third row. Okay, so now let's see if we can answer the question. When do we have no solutions? When do we have one solution? And when do we have infinitely many solutions? Okay. So this 4 minus k squared, I actually don't know what that number is. It would depend on what k is. So what values of k are maybe jumping out at you that we need to think about right now? 2, and what else? -2, right? If k was equal to a 2 or a -2, this would be 0. But actually, if it wasn't, so if k wasn't one of those, if k does not equal plus or minus 2, then would you guys agree that in that case, this would actually be a pivot as well? Now, it might not be equal to 1, but it could be equal to 17, and then you would just multiply through by 1 over 17. The point is, as long as this is not 0 right here, guys, it's gonna be a pivot position. We might have to do another ERO, but it will for sure be a pivot. And if we have a pivot there, let me just, for the moment, let me just circle it. If we had a pivot right there, how many solutions would this system have, the way I've written it here? Exactly 1 solution. There's no pivot going to the far right column, but there's also no free variables. So in this case, we would have exactly 1 solution. 1 solution. So I guess that's actually part B we're answering first. So 1 solution would be k does not equal plus or minus 2. So that's the part B actually. So we're kind of going out of order here a little bit, but that's okay. Let me unpivot that square for a second. If k is equal to 2, let's just go ahead and plug in 2 here into that last row. I'm not gonna worry about the first 2 rows. Just look at the last row with me. If k is equal to 2, then the bottom row becomes 0, 0, 0, and -4. How many solutions would this have? No solutions, right? If you have a pivot in the far right column, that's basically bad news, right? That would be no solutions. So that's this one. K equals 2 would be no solutions. Let me come over here, I guess. And let's try the other one, which is -2. If we put in -2, again, I'm not gonna worry about the first 2 rows. If we put in -2 along the bottom for K, then I'm gonna have a 0, a 0, a 0. And if I have negative of -2 and I subtract 2, I have another 0. So in other words, basically, what we would say is that whole row is gone. And now how many solutions would you have for this system? Free variable right there, yeah? Free variable, and that's infinitely many solutions. So that would be this case, K equals -2. Okay, so it's just a nice problem to kind of review those 3 outcomes of Gaussian elimination and how they should look. So any questions on that? If not, I don't have anything else for today. I appreciate you being here. I will have office hours if you need help. Also, if you have not introduced yourself yet, I'm gonna make next week the last week you can do that. By next week, I'm probably gonna be giving out an extra bit of quiz. So do stop by either in Zoom or in person. I would love to meet you. Have a great rest of your day, guys. Be careful out there. It's a lot of traffic.
Going back up.